And for me, that doesn't always make so much sense when it's written in words, but if I look at it as an example in math, this is going to be, I think, a little more clear. If I said to you 2x plus y equals 10, and maybe y equals 2/5 x plus 4. And so those happen to be two equations that if we stop to graph them, we'd be looking at some lines. Right? So that's all it means to be a system. You're looking at more than one equation at a time, and we're just looking at linear systems. So that means later on in your math career, you might explore systems that have something besides lines in them. So a solution to this would be any ordered pair xy that works in both equations when substituted in. I think I'll catch our breath for a little minute. Probably easiest to just think it makes both equations true. So it's not enough that you just work in this equation, you've got to work in both, if the system has a common solution. And so we're going to have three different ways that we do this. The first one, we can graph them, which I'm hoping that one you're pretty comfortable with. Second one is substitution, which again, I think many of you have probably seen that idea, but just maybe not as formally. And then the last one that we'll look at is elimination. And that's the one that will probably be the newest idea for you. And again, we're sort of speeding this whole lesson up for you. But if you can imagine, if we have two lines, and we want to see, do they have a common solution, there's going to be three things that could happen when you graph them. So I'm going to ask you right now, just for number one, I was kind to you. Both of those equations are in slope-intercept form. Can you graph both of those lines for me right now? So this is a test to see if you remember slope-intercept. See how well your 516 teachers taught you.
Uh-oh.
And if you don't remember, certainly ask somebody sitting right there near you.
Don't embarrass me.
So for this first equation, what's our y-intercept? And y equals 3x minus 1. Brennan?
-1.
Okay, -1. So I'm going to go to -1 on the y-axis. And then what's my slope? Nelson?
3.
3. So I'm just going to write that 3 over 1. So I'm going to go up 3, right 1. Up 3, right 1. Or down 3, left 1. And again, we're going to do the best we can today. So make the best straight line that you can. And now we're going to graph the second equation, y equals -1/2 x plus 6. So now my y-intercept this time is 6. And my slope is -1/2. So I'm going to go down 1, right 2, down 1, right 2. So, turns out in this example, our system had a common solution. Where did these two lines intersect?
2x and 5y.
All right, so that means that 2, 5 is a solution for the system. So this has one solution. That ordered pair is the only set of xy's that will work in both equations. And these are intersecting lines. Now, when we look at example 2, can somebody tell me what form that first equation is written in? Do you remember from last week? Yes. Standard form. So I think Mo had mentioned to you that today you might find out why that form is useful. One reason is it's quick sometimes to graph these. Don't go rearranging that into slope-intercept if you don't have to. Instead, find the x and y intercepts. So, if I made x0 in there, what would y be? 6. So 0, 6 is on that line. Now if I make y0, what's x? 3. Graph those 2 points and you have that line. You don't need to go and rearrange it. So let's plot those 2 points, 0, 6. Oops, I just went the wrong way, 0, 6. And then 3, 0. Again, I think in a minute I'll be going. So if it's in standard form, if you can quickly get your x and y intercepts, it's going to be faster than rearranging. And here, negative 2x plus 2, there's plus 2, we're going to move down 2. All right. So what kind of lines are we looking at this time? Parallel. They ever going to hit? No. So this system, there is no ordered pair that's ever going to work. This has no solutions because we're looking at parallel lines. So that there's no xy pair that would work in both equations. So down here, I've done the same thing. This one's in standard form. This one's in slope-intercept. Can you graph those two for me? For this first equation, if I made x0, what's y? 3. All right. And if I made the y0, what's the x? 2. So again, we've got some nice easy numbers to work with today. So 0, 3, 2, 0. There's our line. Okay, when I go to the next one, my y-intercept is 3. Oh, so there I am, 3. My slope, I'm going to go down 3, right 2. Okay, what the heck is happening here? It's the exact same line, right? So what do you think that means in terms of solutions? Infinite. They're all going to work because you're looking at the exact same line. So this one has infinite solutions, and it's the same line. And actually, one other thing I just wanted to mention before you turn the page there. Just left those drawings up there. But you had said this one had infinite, and it was same line. Or sometimes it might be the coinciding lines. Systems get names whether they have a solution or not. If you have a solution, so this one here had a solution, this is called a consistent system. That means it has a solution. So what do you call the one over here that didn't have a solution?
Inconsistent.
Inconsistent. Did this one down here have solutions? Yeah. It had lots, right? So this one is consistent. But you know us mathematicians, if that one's consistent and that one's consistent, there must be another word I have to use to describe the difference between those two situations. This one only had one solution and this one had lots of them, infinite. So this one is consistent independent. There's only one point that's going to work. This one is consistent dependent.
What if one line has like 6 solutions and another has like 1 million? Are they still the same?
Well, there's only 3 things that can happen when we look at a system of 2 lines. They can only hit in one point, no points, or all points.
Oh yeah, I didn't think of that.
That's okay.
Okay.
All right. So, here's the thing. How many of you love graphing? Okay, I wish there were more hands than that. But if you have to sit there and do it by hand, you don't love it, right? So there's a cool little feature called GeoGebra that I'm going to show you in a minute that can help on the computer to do these graphs for you. But if you turn to the next page, the second method some of you might prefer more than others because it's more algebraic. All right. Well, we're going to talk about the pros and cons of the methods, hopefully. All right. I'm going to do these three really quickly with you because my hope is your algebra skills are right there. So we're going to use substitution instead now. Here, y equals 3x minus 1. Here, y is negative a half x plus 6. They're both equal to y, so we can just set them equal to each other. 3x minus 1 equals negative a half x plus 6. Now you're all back into your equations that you love so much, right?
Yeah.
So let's add a half x to both sides. 3.5x minus 1 equals 6. Add 1. So 3.5x is 7. So what's my x? 2. 2. 3.5 times 2 will get me to 7. So you have the x value of your solution, but this is a system, so you need an ordered pair. So once you know that x is 2, plug it back in. Y equals 3 times 2 minus 1. 6 minus 1, so I'm getting y is 5. So that means 2, 5. To make sure you did your math correctly, I would take the 2 and plug it into the second equation because it's supposed to work in both of them. Negative a half times 2 is negative 1 plus 6, and look at that. Y is 5. And that's the same ordered pair that we got on the front page when we graphed the two lines.